Hello, my wonderful group of Chem 20s. Mr. Jukley here, going to go take us through the next little bit. This lesson is primarily about major entities in water. So when we put stuff in water, what exactly happens to them? So what you'll need for this lesson is your green, if you picked it up from the school, it'd be green, solutions booklet. If not, you can get that on our Google Classroom. It is our solutions unit. If you look at the PDF, that's the one to get. And you'll also need your data booklet. In particular, you might want to have that open to page 6 for the solubility chart. So let's get into it here. The first little bit of this is kind of a review of some of the things that we talked about in the previous lesson. So it's what happens when you put things into water? So we've got the idea of dissolving, dissociation, and ionization. So we talked about, and one of the big things that we talked about is actually, I guess, the second thing down here, what happens when we put ionic compounds into water. And what we actually see is that the individual ions, so there's a sodium ion and there's a chlorine ion, they actually break apart from each other. So it's like the water pulls them apart and breaks the bond between the sodium and the chlorine, and forms new bonds between the positive sodium, that's the thing that's in the middle there, and the negative side, because remember, water is a polar molecule with a partially negative and a partially positive side. So the positive sodium forms bonds with the partially negative side of the water, and it separates and it's surrounded by those water molecules. The chlorine does pretty much the exact same thing. So it gets pulled off, but it's attracted now to the partially positive side, so to the hydrogens. And remember, this is called dissociation. So when we're talking about ionic compounds breaking apart into their ions in solution, it's called dissociation. We should know that. And we should also know, this was the big idea from yesterday, or, well, the last lesson, depending on when you looked at it. We should also have the idea of the balanced dissociation equation. So this one with sodium chloride is fairly straightforward. We see one sodium chloride break apart into one sodium ion and one chloride ion. We saw ones that are a little bit trickier before, but we just need to make sure whatever's going in comes out. So that is dissociation. We talked about this one a little bit as well. Well, the first one, the top piece up here, is what happens when we put molecular compounds into water. And if they are highly soluble, they do dissolve, but they don't break apart necessarily. The individual molecules stick together. So you might have, a block of sucrose. This is a sucrose molecule that we have over here. You might have a big chunk, and each individual square represents an individual sucrose molecule. When you put that into water, they just separate into their individual molecules. And each individual molecule, that's what we see on this side over here, each individual molecule is now surrounded by those water molecules. So typically, molecular compounds, what we say is that they separate in water. So ionic compounds, if they're highly soluble, they dissociate, whereas molecular compounds separate into individual molecules. Now, the other part of this one that we've got here is if it's a molecular compound and it is separated, it's still an individual molecule. There's no actual charge. There's no actual positive or negative. It is electrically neutral particles, and therefore they do not conduct electricity. So do not conduct electricity. Whereas when we look at our ionic compound, because it's breaking apart into actual positives and negatives, cations and anions, it does conduct electricity. So conducts. Now some of you probably, and I think we've mentioned this before, conducts. I got messy. Let's start again. Conducts electricity. Just like in class, I should finish what I'm writing before I start talking about something else. So yeah, and for those of you who have learned about electricity, all electricity is just moving charges. So it's pretty easy to see how an ionic compound can conduct electricity if we've got charges, and if those charges are easy and free to move around. Perfect. So that's those two. We will talk about the acid-base ionization in a second here, but one exercise that we've got with this, and this one we're not going to go through in a ton of detail ever here, but if you want to check this one out, if you want a bit of extra practice, absolutely feel free. This table 5 is a very nice summary of some of the things that we've talked about, in particular the conductivity. So metals, right, and again, this is all about conductivity. So when we talk about metals, when they're solids, they do conduct electricity. When they're liquids, not so much. And then when they're aqueous, well, do metals dissolve, I guess is the question. They just don't dissolve. Like picture taking a piece of silver jewelry or something like that and putting it in water. Is it going to dissolve when you put it in there? No chance. Don't dissolve. So I'll put that for that as well. Nonmetals, so elemental nonmetals, same thing, except, well, they don't conduct electricity when they're solids, they don't conduct electricity when they're liquids, and they don't dissolve, so they don't become aqueous solutions. Then we've got our ionic compounds. As solids, they don't conduct. As liquids and as aqueous solutions, they do. Excellent. Molecular compounds, just no's across the board. They do not conduct electricity. And acids, when they're solids, nope. That's the wrong thing. Nope. When they're liquids, nope. But when they're aqueous, yes, they have ionized and they give us that hydrogen ion is the definition that we have at this point. We'll change that in a little bit, but for now, that's what we've got. Perfect. So using this table, go through and see if you can figure out what chemicals 1 through 7 are. So the chemicals are listed. We've got potassium chloride, barium hydroxide, what is C6? Yeah, what is that? C6H5COOH. I believe that's benzoic acid. We got solid zinc, so that zinc is a metal, calcium phosphate, and the list goes on. So see if you can use their properties. So figure out, ideas with solubility, ideas with conductivity, again, for those major classifications, metals, nonmetals, ionic, molecular, and acids. And then also talking about red versus blue litmus. You might remember that acids turn litmus paper red and bases turn litmus paper blue. So if you want to check this one out, that is A-OK. Next piece, though, that we're going to look at together here is getting into the substances in water. And just big thing with this, there's lots of things that don't dissolve in water. There's lots of things that do dissolve in water. Remember, and this is one of the things that we'll look at again, for ionic compounds, we can use that solubility chart. Acids also dissolve, but they also vary in their electric conductivity. Acids are good conductors, or if acids are good conductors, they're said to be strong acids. So good conductors are strong acids. Examples of strong acids are listed right here, and they're also listed on page 8 and 9 of your data booklet. So you can check out acids, page 8 plus 9 of data book. Nice, and I might even pull that up for a split second here. Where do we have it? I believe it's this one. So let's go to page, it's sideways. That's a little unfortunate. But page 8 and 9 of our data booklet. So pretty much anything from here up, we would call a strong acid. And pretty much anything from here down, we would call a weak acid. And then you may remember, I believe we talked about this in the last lesson, you may remember that strong acids, I'm going to abbreviate this, strong acids ionize 100%, and weak acids, let's abbreviate it as well, weak acids ionize less than 50%. So when we say ionize, that means break apart into their hydrogen ion and whatever other anion is left over. So strong acids, 100% break apart into hydrogen ions, whereas weak acids, not so much. Nice, so that's a bit of a review, and we've kind of seen that before. Going Going into the next little piece here, and this is the big part of today's lesson. The following tables should be memorized. You should have an idea of this, and it's really not too difficult. It's not that much of a stretch of what we're talking about before. It's all about the major entities present in an aqueous solution. So when we think about what that means, the major entities present. Major means the biggest kind of thing, right? So what are the biggest entities? Entities are the substances, or what we'd actually see, the parties that are involved in this aqueous solution. So what exactly is in that aqueous solution? So we can go through and look at this. One thing that I'm pretty sure is listed somewhere up here. Yes, here it is. When we're talking about our major entities, if it's an aqueous solution, it's always water. So always include H2O as one of the major entities for an aqueous solution. So let's go through and let's check a couple of them out. For ionic compounds, we've got two options here. We've got things that are highly soluble, and if they're highly soluble, they're going to break apart into their positive ion and their negative ions, their cation and their anion. So for this example, we've got sodium chloride. It's going to break apart into sodium ions, chlorine ions, and of course we've got water. So those are the major things that are present. If I were to draw that out, I have, let's use some blue for water. Very nice. I've got a beaker full of water, and then I've got sodium chloride. So I put sodium, maybe I'll make green, and chlorine, maybe I'll make red. It doesn't really matter. They are clearly attached together when they're there. When we put them into the solution, they break apart into separate sodium and chlorine. So they break apart. They're there. They're the major entities along with that water. But then if I were to take my calcium chloride, so calcium, or sorry, not chloride, calcium carbonate. So I've still got that beaker full of water. Obviously, water is one of the major entities, so the blue dots will represent water. And then if I take, let's choose a couple different colors here. So I've got calcium, which I'll draw in black. And let's pick a random color for the other one. Let's pick that green. That's a nice green. And I've got my carbonate here. When I put those into the solution, so I dunk those into the solution over here, it's realistically going to stay just as calcium and carbonate. Like, it's not going to dissociate because it's low solubility. So yeah, that's sort of the scoop with that one. If it dissolves well, it breaks into its ions. If it doesn't dissolve well, it stays mostly as a solid with water. Cool. Next one, bases. Well, bases, you probably remember, are just ionic compounds that contain hydroxide, or at least that's our definition for right now. So again, we check the solubility table. If they're high solubility, well, it breaks apart into its ions. If it's low solubility, it stays clumped together as whatever ionic compound it is. So in this case, calcium hydroxide stays as mostly solid calcium hydroxide. Nice. And of course, we've got water. It's one of the major entities in in an aqueous solution. For molecular substances, it's a little bit harder to predict the solubility, right? So we don't have that solubility table on page 6 for molecular compounds. You might remember from the bonding unit with aqueous solution, so aqueous dissolving in water, it typically dissolves our polar molecules and our molecules with hydrogen bonds the best. Low solubility, we'll typically see nonpolar molecules like methane and octane. So for high solubility, it separates into individual molecules. Big thing is we're just calling it aqueous, and obviously water will be there as well. If it's low solubility, so let's say that I put some like canola oil or something like that. We've all seen canola oil, and I put it into water. It's not actually going to dissolve in water. It's just going to stay as whatever state it was in before. So sugar, this top one is sugar. I think that one is sucrose, actually. You put that in water, it dissolves, it becomes aqueous sucrose. You try and put oil or octane or methane into water, it's just going to stay exactly the same way. It's low solubility. So major entities there. For strong acids all have high solubility. And remember, we just looked at our data booklet to see which ones were strong acids. So strong acids all have high solubility, so they all break apart into their ions, one of the ions being hydrogen, and then whatever anion balances that one out, and obviously water is involved as well. For weak acids, those are ones with low solubility. This is where it gets a little tiny bit trickier. Weak acids, they have lower solubility in terms of, or ionization, but they can still dissolve sometimes fairly well. So oftentimes we still see them written as aqueous, right? But they're still technically molecular compounds, so they still, for the most part, stick together. So for example, hydrogen acetate sticks together and stays mostly as hydrogen acetate, or acetic acid, if you will. And then finally, last one that we've got is elements. Elements all have low solubility. Every single one of them has low solubility, so it stays as the atom. So for example, you take some solid copper, you put it in water, you've got solid copper in a jug of water, right? You take some solid zinc, you put it in water. You've got solid zinc in water. You bubble some nitrogen through water. You've just got nitrogen bubbles in water. They do not dissolve. They're very, very low solubility. Perfect. So this is something, this chart, like it's quite the chart, but when you look at it, it's actually not that bad, right? It's definitely not that bad. So know what happens to different types of compounds when you put them in water based on their solubility, and know the major entities or the major things that will be present in that solution. So let's check out a couple examples. Determine the major entities present when aqueous solutions of the following are made. So we're trying to make solutions out of each of these. So things that I would go through and check out and try and get a hold of. I'd go through and I'd say, okay, ammonia. First off, what is ammonia? It is NH3. Is it a molecular compound? Is it a ionic compound? Is it an element? I believe ammonia is, oh, it might be a liquid actually. No, I was right. Just double checked. It is indeed a gas. It is a molecular compound. And it is a polar molecule. So from all of those things, we could say if it's a polar molecule, it likes to dissolve. It's molecular, so even if it does dissolve, it's just going to stay as its individual molecules. So the major entities present would be NH3, but it would be now dissolved. So we put aqueous afterwards. Let's try that one more time. And we would also have, of course, water, H2O, as a liquid. Perfect. There are major entities present for ammonia. Let's check out number 2. So barium hydroxide. First, I should probably figure out what barium hydroxide is. BaOH, oops, I almost screwed it up there, 2. Now, if I want to figure out what happens when I put this in water, I'd first off recognize this as an ionic compound. You might even look at it a little bit further and say that it is not just any ionic compound, it is a base, and we know that because it ends in hydroxide ion. So in order to check, we need to go to our page 6 of our data booklet. So get out our data booklets, flip to page 6, and it was barium hydroxide. So first step, I got to find one of my 2 ions across the top. Oh, hey, there it is. There's hydroxide. Very, very nice. Now I got to go down and I got to figure out, okay, well, is it going to be high solubility? Is low solubility? So I start scrolling down. I say, okay, is barium in group 1? No, barium's in group 2. So then I keep scrolling down. Oh, ammonia. Well, that's not the same thing. It's neat, but it's not the same thing. So if it's not in group 1 and it's not ammonia, it means it falls under most. Nice. And if it falls under most, that means it's going to have low solubility, so we're going to leave it as a solid. So let's go back to the table here, and let's say if it's staying mostly as a solid, we're just going to have barium hydroxide, and we're going to have H2O liquid. So solid barium hydroxide, like a clump of the powder in the bottom of whatever vial of liquid water we've got. Cool. So that's not too bad. Aluminum metal. So aluminum metal is just Al solid. It's an atom, right, or an element. So for this one, fairly straightforward. Elements all have low solubility, so it's going to be Al, and it's just going to be a solid piece of aluminum in some liquid water, H2O liquid. Nice. Kind of getting a little bit messy here. Let's do one or two more of them. Let's do magnesium phosphate. So magnesium phosphate. So I believe that's Mg3PO4 2. So we're balancing out those those charges in that one to make sure we got the correct formula. So this one, again, it's an ionic compound. So it's ionic that we're dealing with here. So if it's an ionic compound, I'd better go ahead and check this. Maybe I'll clean this up a tiny little bit. Excellent. And we'll go back. So we're looking for either, shoot, I forgot what compound it is. We're looking for magnesium phosphate. So I scroll across the top looking for one of the two things. Oh, hey, there's phosphate. Very nice. And then I scroll down. Well, magnesium is not in group 1. It's not NH4, so that means it must fall under most. And again, that's low solubility, or we're going to say it's a solid. Okay, no problem. So go back to here. Get my nicer felt pen. There we go. And this is going to be, let's see, Mg3PO4 2, so my magnesium phosphate, and it's just going to stay as a solid. And let's see, I'm going to have H2O as my other entity. So that's not too bad. Ooh, a couple acids to finish things off. A couple acids, very, very nice. So hydrochloric acid. That's HCl when we're remembering our naming rules. So the hydro tells me that it's going to be just an element off the periodic table. The chloric tells me that it's going to be dealing with chlorine, and the acid tells me it's HCl. So that one's going to be, I believe that one's a gas when it's all by itself. It's an acid. So I just got to think to myself, okay, is this one a strong acid or a weak acid? So again, I go back to my data booklets. I go over, page 8 and 9, and I'm searching for hydrochloric acid. So it's a little bit sideways for me here, but I think I see hydrochloric acid right here, and it is definitely above that gray line, so it's definitely a strong acid. Very, very nice. So I just say strong acids ionize 100%, so it's going to ionize into H plus and Cl negative. And of course, H2O as a liquid. H2O is always one of the major entities. Last one here, sulfuric acid. Again, I got to check sulfuric acid. Is it strong or is it weak? So we search the table over here. Got to turn my head totally sideways. Oh, there it is. Actually pretty easy to find. So sulfuric acid is definitely on the weak acid side of things, which means that, well, it might still dissolve. Weak acid. Oh, and I should have put strong acid for that other one up top there. Strong acid. So it's a weak acid. So it's going to dissolve, but it's not necessarily going to ionize that much. So I'm going to put that in as H2SO3 aqueous plus H2O liquid. So those are my major entities in water. And we might circle each of these just to keep them a little bit separate. Sorry, got a little bit messy here, folks. A little bit messy. But our major entities in water are all circled there for each of the examples. Cool, so I hope that makes sense for you. You got a bunch of practice here. Let me just see here. It is page 11. I think it's, no, that can't be right. Yeah, no, it is page 11. So everything from 1 and then up to P. So this is sort of what I really want you to do, everything, page 11 and 12, O to P. If you want to check out, again, this is one of those optional things, and remember, all of our stuff right now, it's about the learning. So what do you learn from this, as opposed to thinking about any assessments at this point. But so if you want to check this one out, you can also check out the lab exercise, the qualitative analysis. So you got 5 different solutions, and you're trying to figure out which solution is which based off of its effect on litmus paper, its conductivity, and its pH. So sort of similar to the last optional lab that we had right there. So that is the lesson for now. We'll come and we'll pick things back up soon enough here. So good work, Chem 20s. We will talk to you again soon. Bye for now.